All right, so picking up where we left off here with example number 7. Sorry, I'm trying to go full screen here. There we go. So picking up, like I said, where we left off here. Example number 7. Get rid of that. All right, so our task here is to find the product of CD. So remember, before we actually start multiplying anything out, it's going to be wise for us to figure out whether or not it can be done. So we know that matrix C has order 2 by 2, matrix D has order 3 by 2. So remember, in order to pull this off, the middle numbers have to match, and very clearly they do not match. So the product of C, D is undefined. It's not going to work. Literally could not do it. So the follow-up question to that is, can you find the product of DC? Well, that's going to change some things, specifically the order. So now matrix D, my 3 by 2, times matrix C, my 2 by 2, that's going to change enough to where now, yes, the middle terms do match. And I understand that we're going to be creating a 3 by 2 matrix. So again, knowing that we're building a 3 by 2 matrix, again, call it personal preference if you'd like, but I know that I would prefer to see the values written out, or the matrices, excuse me, written out in the proper order. So matrix D is -4, 5, 7, 0, 2, -1. We're going to multiply this times matrix C, labeled up top, matrix C, which is 3, 5, -2, 4. So as we claimed here, we know that we're going to be building a 3 by 2 matrix. So again, my template here, 3 by 2, 3 rows by 2 columns. We're going to be looking to build something of this nature. So, all right, sorry, getting back to this one. So again, if my target is row 1, column 1, that means quite literally we're going to multiply row 1 times column 1. So setting this up, row 1 times column 1, we're looking at -4 times 3 is -12, 5 times -2, 5 times -2 is -10. Row 1, column 2, first elements, -4 times 5 is -20, 5 times 4 positive 20, so -20 plus 20. Row 2, column 1, 7 times 3 is 21, 0 times -2 is 0. Row 2, column 2, first element, 7 times 5, 35, plus 0 times 4 is 0. Row 3, column 2, or excuse me, row 3, column 1, sorry about that. First elements, 2 times 3, 6, -1 times -2, 2. And then finally, row 3, column 2, first elements, 2 times 5, 10. Second elements, -1 times 4, -4. So now to actually find the sums, throwing markers all over the place. So to find these sums, my 3 by 2 matrix, again, what we claimed was DC. That was going to be like -22, 0, 21, 35, 8, 6 is happening. So again, lesson hopefully that we're picking up is that the commutative property does not exist with matrix multiplication. Okay, so like in dealing with numbers, 3 times 5 is the same as 5 times 3. Dealing with matrices, it doesn't work like that. Again, we were not able to do CD. Again, C times D was undefined, whereas D times C led to this 3 by 2 matrix. All right, so next up, we're going to alter the directions here a little bit. Instead of finding the product, which I think we're probably feeling pretty good about, what we want to look at is, first off, can we multiply, and what's going to be the dimension or the order of the resulting matrix if we were to multiply. So part A, we have a 2 by 2. I'm trying to multiply this times a 2 by 3. So the first question, yes, we absolutely can multiply these. Again, my middle terms match. But more importantly, we've got the outer terms. They tell us that we're going to be obtaining a 2 by 3 matrix. Okay, same thing in part B. Here we have a 3 by 2 matrix times a 2 by 1 matrix. So again, first up, yes, we can do this because the middle terms match. And furthermore, we can see that we're creating a 3 by 1 matrix. All right, lastly, in part C, we have a 2 by 3 times another 2 by 3. So in looking at the middle terms, unfortunately, they don't match. So no, we cannot multiply these matrices together. And since we can't multiply the matrices together, then there is no resulting order or anything like that. All right, now, like I talked about in class today, I made the mistake my first year of teaching pre-calculus, working with matrices. I screwed up assuming that, oh yeah, everybody understands what it means to square values. And while that's true, we didn't necessarily make the jump to understanding what it meant to square matrices. So if you have the number 5 and you square the number 5, understand that that literally means that you're going to take 5 times 5 to obtain 25. Just like if you have x and we're squaring it, that's equivalent to x times x. If you have x to the 5th power, that's x times x times x times x times x. Again, that's what exponents are telling us to do. It's no different with these matrices. Again, if we have matrix A, we literally are going to multiply matrix A times matrix A if we're obtaining A squared. So again, as long as we're disciplined enough to recognize that if I have matrix A, for instance, down here and I want to find A squared, I'm literally going to turn it into a multiplication problem where I'm going to take first matrix A times the second matrix A, and now I have a 2 by 2 times a 2 by 2. So yes, we can do this, and we're going to obtain our answers this way. So again, we know that we're going to be building a 2 by 2 matrix. And in doing so, targeting row 1, column 1 means that I'm multiplying row 1 times column 1. So row 1 times column 1, first element is 5 times 5, 25. Second element is negative 2 times 3, negative 6. Row 1, column 2. Row 1, column 2. I'm going to take first element 5 times negative 2, negative 10. Second element, negative 2 times 1, negative 2. Now we're targeting row 2, column 1. So we're going to multiply row 2 times column 1. So first element is 3 times 5, 15. Second element is 1 times 3, 3. And then finally, row 2, column 2. Now we're multiplying row 2 times column 2. First element, 3 times negative 2 is negative 6. Second element, 1 times 1 is 1. Combining these to obtain our product, 25 minus 6, 19. Negative 10 minus 2, negative 12. 15 times 3, 18. Negative 6 plus 1, negative 5. So it looks like A squared is equal to this 2 by 2 matrix. All right, so the reason why we point this out, possibly maybe could have made this connection on your own, is that a lot of students in past years have wanted to look at this and say, oh, you're squaring the matrix? Simple. Let's just square all of the terms. Now, understand that that is not equal to A squared. That's not true. Again, what this would have led to, 25, 4, 9, 1, this incorrect matrix is very different than the correct one down here. So please, if that's what was popping into your head, push it out right now, because that is not the way that we square matrices. Again, we have to remain disciplined enough to actually recognize that matrix A squared means that it's going to be matrix A times matrix A. Again, which should not come as any bit of a surprise whatsoever, as that's what it means to square numbers, so that's what it should mean to square matrices as well. All right, last type of problem. As addressed here, this is way more of a section 8.3 thing, in my opinion, than an 8.2 thing, but here we are. Again, I would say that 8.2 really, the whole reason why section 8.2 exists is so we can utilize it in 8.3. So really, they're somewhat blended. It's in many ways, in my opinion, just it's just the continuation. So again, 8.2 and 8.3 in my mind is kind of just one big giant section. We just had to break it somewhere. So the most complicated thing about this example number 10 is going to be the terminology, the wording, the way that things look. But the math is, I promise you, really is not that bad. So we start off in a familiar situation where we're given a system. What may be a little unfamiliar, and no, this is not always going to be the case from here on out, but what may be a little unfamiliar is that we're very used to seeing a system with two variables, two equations, to have the two variables x and y. This has x1, x2. Please don't let that throw you off at all. Again, quite literally, that's not even going to factor in for us and for our purposes. Okay, so we have two tasks here. First thing that we're asked to do is to write the system as a matrix equation, ax equals b. Now, this is going to be a big deal for us moving forward. This whole notion of we're going to solve what we call matrix X. But before we do that, we have to understand what the parts are. So matrix A, the first thing that we're supposed to do, or find, that is what we would call the coefficient matrix. So the coefficient matrix, we've already discussed, and again, hopefully if there's one that we feel familiar with, it's the coefficient matrix. So the coefficient matrix means that we're going to look at the left side of my system, and we're going to literally form a matrix out of these coefficients. So we have the coefficients -1 and 3 in my top row, +1, -1 in my second row. But this is what we would refer to as the coefficient matrix. All right, so now the new one, matrix X, like I said, brand new, haven't talked about this before. This is what we call the variable matrix. So the variable matrix is exactly that. It's going to be the variables. So as we look up here, the variables that we have are x1 and x2. So this is what it's going to be referred to as the variable matrix. And then finally, matrix B. Again, I know that I don't believe that it's shown up in the notes, but I know that I have talked about it. But matrix B, that's what we're going to refer to as the constant matrix. So the constant matrix, it's literally going to be your constants. So 3, 5, 3. So if our task was to figure out A times X and set that equal to B, then we just need to put some signs in here. We're going to say matrix A times matrix X equals matrix B. So in part A, or the first part, the initial part, that's what we're supposed to do. And we're finished with that first initial part. Again, if we're calling like this is part A and this is part B. Okay? So setting this up, we'd make the argument that's the key. Now, where we're going with this in the very near future, like section 8.3 tomorrow, is that we're going to be multiplying by both sides by the inverse of matrix A, which is very comparable to dividing. But again, it's not quite the same thing. So now here in part B, what we're asked to do is to use Gauss-Jordan elimination on the augmented matrix A augmented with B to solve for matrix A. And sorry, as I was reading that, I remembered that I had one other thing that I wanted to talk about. And that was right here. The coefficient matrix, the way that we built that was, I mean, we didn't really have any choice. Again, that's how it was going to look. But for the variable matrix, we have two matrices. Why in the world would I have made that a column matrix instead of a row matrix? Meaning, why did I write it vertically, not horizontally? And it's because we're trying to multiply. Okay, so I currently have a 2 by 2 matrix. And when I set it up this way, that means that we have a 2 by 1 matrix. Yes, we can multiply that. If I would have set it up differently as a row matrix, meaning that if I would have set that up as a 1 by 2, then we would have had a major problem on our hands, like we literally couldn't do this. So please understand that we're always going to set it up as a column matrix because the multiplication has to work out. All right, so now for part B, what we're looking to do is to augment matrix A with matrix B. Now remember, to augment sounds fancy. We're just going to put them together to create one matrix. So we have matrix A, which is -1, 3, 1, -1. We're going to augment that with matrix B, which is 3 by 3. Then it says to use Gauss-Jordan elimination. That's just your row operations. We're going to use that to figure this out. So that means that we want to turn the left side into reduced row echelon form, the 1, 0, 0, 1. A lot of different ways that we could get there. I know that typically we would start at that top left corner, row 1, column 1, but I'm actually going to start here in this particular case. And I am trying to move quickly as I have like a minute, 10 seconds. So first row is going to stay the same. Second row, though, I'm trying to create a 0 in that spot, so I'm going to say that row 1 plus row 2 should get us there. So -1 plus 1, 0, 3 plus -1, 2, 3 plus 3, 6. All right, so now we do need to clean this up. We can't leave that as -1. It worked out very nicely for us on the previous problem, but we need that to be a +1. So my second row stays the same. My third row, though, or first row, excuse me, I'm going to multiply a -1 through. So basically just change the sign. That's going to become 1, -3. As we continue on, my next target is going to be this 2. All of a sudden, my smart board decided not to work anymore. There it goes. So we need to turn that 2 into a 1. So I'm going to multiply the entire second row through by 1/2. So we're going to go 1/2 of row 2 and obtain 0, 1, 3. And we're in row echelon form. We need to reduce row echelon. So that means, targeting one more spot here. Looks like we're going to do 3 times row 2 plus row 1. And that should get us 0, 1, 3.